In this question, we're going to talk about what is a string, what is a rope, what is a prefix tree. Let's take a look at something that is slow. If we have a Python string and we append to it in a loop, that tends to be slow. And it tends to be significantly slower than doing a join operation, so much so that in the Python sum function, they even eliminated the ability for you to sum strings because this is just so slow in practice. You can see how bad this is, 2 seconds for this size versus 0.0 seconds. But you can see the behavior is about roughly the same in the sense that it seems to be varying on the size of the data. So it's either linear or linear arithmetic or maybe even quadratic, but at least it's definitely not constant time, and it's definitely not, logarithmic in time. Now, what we can see from this is, there's a reason why sum says you can't use strings, even though you can basically comment this out in the CPython source code and allow yourself to do it. Well, the reason for that is it's just operationally slow. But we're not talking about operationally slow things here. We're talking about analytical risk management of things that are theoretically slow. And so let's try and look at another operation and see if something else could be assessed for being critically slow. Here, in this operation, what we're doing is we're trying to mutate a string. And since the string is immutable, we can't mutate the string in place. What we can do, however, is take all the elements up to the point we want to mutate, perform a mutation, then take all the elements from that mutation point to the end, and then rejoin this back into some structure. And that's going to be pretty slow. And you can see the slowness here. There's a problem when we try and mutate strings. They're not really meant to be mutated in this fashion, and so this just tends to be pretty ugly. And this leads to at least one of the data structures that we want to talk about. But I want to share with you another example of something that we might run into as being slow. Let's say that we have a collection of strings, and we want to identify if a string is in that collection. Well, that's actually pretty fast using the set. And in fact, we know that the mechanism behind the set is very similar to the mechanism behind the dictionary. It was very similar to the mechanism behind the pandas categorical. And we know that this is constant time. We know this is pretty fast. But what if we don't want to find an exact match? We want to find a near match. We want to find the value that is of closest match. And this has come up before. This has come up when we try and solve problems like Scrabble or problems like crossword or problems like jumble. We may want to find what is the string that matches as close as possible to this target string. And when we do that, we can think the set simply does not contain enough information to tell you whether something is a close match or not. It can tell you very quickly if something is an exact match, but it can't tell you if something is a close match. And if we needed to do closest matching as fast as can be, fundamentally the structures that we have are not fast enough to do it. They just don't have enough information. And that may lead us to what information do we need? Well, what we need is some way to quickly identify if a partial match met. So we need to be able to quickly identify if you matched up to some particular point. And we need to therefore represent up to some particular point in the data structure. We need to be able to break down a string into its constituent parts and say, okay, you met up to here, but no further. If this is for a spell checker, for example, we might even want to say, what's the closest match and what are the things that follow up from that? Like if we're doing some sort of auto-completion, we might want to say, if you've typed A, B, C, D, what are all the possible things that might come after that? So we need to store that as well. And the way in which you can store this is with a data structure called a prefix tree or a tree with the IE. And the implementation of the tree is actually fairly straightforward. You can see here we're going to implement this using our network X digraph. And in this network X digraph, what we're going to do is every time we append an element, or when we append an element, we're not going to append these strings as just complete, concrete, atomic strings. What we're going to do is we're going to break them down into their constituent parts, probably into their individual Unicode code points or their individual characters. And we're going to store each one of these elements, because we know if we're going to do some sort of closest match, we need to be able to look at some subset of these quickly. We're going to arrange these in a tree. And the way we're going to arrange these in a tree is we're going to arrange these in a tree where they overlap. So if I wanted to store the string ABCD and ABCE and XYZ, what is the most compact way I could store these? Well, I could store ABCD all by itself. Then I could store A linked to, or I could store A linked to BCD. Then I could store A linked to BCE. Or I could break this down even further, and I could say I'll link this to this in a tree, and you can see I'm reading this from left to right. And I could really store this very compactly with just the difference at each stage. So here you can see I have something like that. Or if I wanted to make this just a little bit easier for myself, I could even break this down into the individual characters. And then I might say, oh, the x, y, z is a little bit difficult. I probably have to start this from a new root. And so what you might think is, the way that I might implement this is with some sort of tree that is rooted on some sort of sentinel value, like here an empty string, off of which the nodes of this tree are merely the individual characters, which as you read from the root to the leaves, correspond to each one of the words that we have stored. And so here you can see we stored A, B, C, D. If we followed this path from this root to this element, you see we store A, B, C, E. And if we followed this path from this element to this element, you can see we stored X, Y, Z. And this structure can then efficiently identify what the closest match is or what the auto-completion would be, because all we have to do is for some particular user input. Like if the user says, I've typed AB, you just follow down the path of this thing. Okay, follow down the A, follow down the B, and then whatever subtree you get is all of the remaining possibilities. And if you can't follow that path, then you know that there is no possible closest match, or you know where the closest match happened to have ended. So if they say, I want to find A, B, C, X, well, you know that the closest match ended at this node because there was no corresponding X to follow up. And that's exactly what the implementation of this is. In the append to add an element, all you do is you traverse this tree down its nodes to figure out where is the anchor point where the commonality is no longer met. You can see we just go down the nodes until we see that there is no corresponding or common element. And then we just insert the rest of what we see from there on. For the nearest match, it's very easy. We just follow the process down this tree in order to figure out how far did we match. And the implementation is so simple, but actually quite helpful for solving these problems and some other problems that have come up in problems like the Scrabble, the Wordle, the crossword, and the jumble. In this particular implementation, we are relying on network X, and we are relying on certain characteristics of network X, like going from one node to all of its children node or all of its neighbor nodes is a fast operation, which, because network X is implemented as a dictionary of dictionaries, is going to be as fast as a dictionary lookup, which we've already seen so far is probably going to be constant time. And so what we can think is the time complexity of this would just be on the time complexity of the length of the number of elements, as opposed to what we would have to do previously, which is look at all of the elements in the underlying structure. And we can see the implementation of this, very simple, missing a lot of core details, but we can append A, B, C, D, A, B, C, F, X, Y, Z. We can look at all the edges, and we can see the edges exactly as we think, from the root to A, from the root to X, from A to B, B to C, C to D, C also to F, and then X, Y, Z as well. And then we can see that it's able to find things like the path to the nearest thing. This is the path to A, B, C, D, which is stored exactly, or the path to ABCX, and it tells us how far it's able to traverse before it can no longer traverse. And so if we had typed ABCX, this might be a possible completion, or if we had just typed ABC, we might even write something that takes this nearest, and instead of yielding those, gives us the completion for this. So instead of yielding these, we'll do something like return self.storage node. And actually, we should store the path as we go, like this, because you probably want that path as well. So here, you'd probably do something like this. And here, let's see if that works. If we asked for the completion for this, you can see the completions for this are, and I guess this is has to be like this. There's multiple possible completions, so we probably have to do something like this. And of course, we'd have to follow those all the way down, but you can see here it gives us, A, B, C, D, and A, B, C, F. We'd of course have to follow these a little bit further, so we'd have to traverse this all the way to the end and do the combinatoric expansion as we see that branch. But you can see at least a very simplistic implementation if we're up to the very last letter.